Okay, we're happy to have Martin Möller, who will tell us about smooth compactifications of strata revealing differentials.
Thank you. Thanks for the invitation here. Nice conference. And I have to warn you in advance that I'm compactifying strata of the moduli space of, well, translation surfaces, flat surfaces, and there will be no representation varieties nowhere. So it's slightly tangential to what seems to be the core of that conference, but it shares interesting features. We have seen those flat surfaces appearing, for example, in Chris Leininger's talk. I'll redraw his pictures. And concepts such as the Lyapunov exponents in the preceding talk by Simeon have been studied in that world. And maybe you will be appreciating the way things are compactified, and maybe this has some applications. So before I go and report on joint work with Matt Bainbridge, Dawei Chen, Quentin Gendron, and Sam Gruszewski, I'll be compactifying the moduli space of curves of genus G. Genus G, also known as MG, and of course, this is just a review of what Delaney and Mumford have been doing in 1968 or 9. So the moduli space of curves of genus G, or Riemann surfaces, is not compact. You often do want to have a compactification. For example, if you want to have enumerative properties that can be calculated by intersecting objects on the moduli space. In order to these intersection numbers to be meaningful, you want it to happen on a compact variety. The original motivation of Delaney and Mumford was to study the irreducibility of that moduli space. And so having a compactification might be useful for topological reasons. So what did they do? So the moduli space of curves sits inside the moduli space of smooth curves. Smooth curves sits inside the moduli space of stable curves. So let me recall you what a stable curve is, where if a smooth curve looks like that. On a stable curve, a certain number of cycles have been pinched off. For example, this one has been pinched off to form geometrically a picture that looks like that. Or you might have several collections, a whole multi-curve, disjoint collection of curves that might have been pinched off. So stable curves are formally nodal Riemann surfaces with the property that the automorphism group of such a curve is finite. So meaning that we disallow components which just consist of projective lines of 2 points, basically. Let me, along the way, introduce the so-called dual graph. The dual graph of a stable curve consists of making a dot for each irreducible component. So if the stable curve happens to be smooth, the dual graph is particularly boring. It's just a point. And also in that case, since the resulting curve is still irreducible, it's just 1 point. And for each node of the curve, here I have one node, I'll draw a loop connecting the components of the dual graph. So in that case, the dual graph looks like that. Second example, if I pinch off the orange curve, the resulting surface looks like that. And the dual graph now has two dots for the two irreducible components and one edge joining the two. So I'd like to say that the moduli space, which is of dimension 3g minus 3, is a complex variety of dimension 3g minus 3. Well, almost. If I'm saying here complex variety of dimension 3 or a smooth complex manifold of 3g minus 3, I'm using a lie that I'll be using all over the talk. Of course, all of you know that there's curve with automorphisms and that these automorphisms create trouble here. So if I say smooth, then you should hear smooth orbifold, or if you want, the true complex structure has finite quotient singularities where you had something or where something smooth is sitting on top of it and you quotient by the corresponding automorphism group. So it's not strictly speaking smooth, but first of all, it's not far away from that, and second, the non-smoothness has geometric origin. It comes from really structure properties of the moduli space of curves. And in that sense, also on the blackboard over there, what I'll be talking about, I'll be abusing the word smooth, and I'll be explaining that in a minute in more detail. So the moduli space of curves of genus G is a smooth variety of dimension 3g minus 3, and this is adding the stable curves. That thing is compact, and if we add punctures, then the dimension increases by 1 for each puncture, and the same procedure works in the same way. Stable curves are curved with n marked points, and the marked points are not allowed to coincide, even at the boundary. If the points want to coincide, don't let them coincide. Take an extra component and put the curves over there. Okay, let me go to that blackboard and introduce to you the moduli space of flat surfaces. So on top of the moduli space of curves, we have well, you could call it total space of the Hodge bundle. So this is the set of all pairs consisting of a Riemann surface X of genus G, and omega, which is omega is a holomorphic one form on X. And if I should be careful and put a star here because I really want this to be a non-zero holomorphic one form. I'm removing the zero section in here. This object, for now, is pretty boring. This is a vector bundle of rank G, because the space of holomorphic one forms for a given Riemann surface is a vector space of dimension G, and since I removed the zeros, so this is minus the zero section. A holomorphic one form on such a Riemann surface of genus G has 2g minus 2 zeros in total. So these zeros can be either all simple or all can come together to just one point, and everything in between can happen as well. So this gives a stratification. Of that whole space, which this is the moduli space of flat surfaces the title is referring to, and I call this strata omega mg mu, where mu is a partition of 2g minus 2. This is a stratification. Of course, these strata are not compact. The moduli space hasn't been compact. Well, points, if you're in a stratum where you have 2 or more zeros, the zeros could collide and you're leaving that stratum. That's the second source of non-compactness. So the name of the game is compactify strata. Let me briefly, because I don't want to, get to that, some motivation. Well, one motivation is enumerative geometry, computing invariance geometry. Computing invariance often and best happens at the boundary, which also brings me to a brief history of what people have been doing in order to compactify that moduli space. So probably the first attempt of compactification, no, not attempt of, it's successful, but it's partial. So Eskin, Maser, and Zorich, we're trying to compute an invariance called Siegel-Veitch constants for these, and they provided a partial topological compactification, saying what the codimension 1 objects are that should be added to the boundary. Way more and in much more detail, a partial or maybe complete, depending on which cases you are, compactification was done by Mirza, Kani, and Alex Wright. Maybe with a precursor in work of McMullen, who has the same idea, which I'll be referring to. McMullen's work was in low genus only. This compactification I'll be referring to, for reasons that will become clear, as the what you see is what you get compactification, which is a word that's pretty hard to write on the blackboard. This compactification is pretty successful in the sort of the second application, namely the so-called SL2R orbit closure problem, and was for them the main motivation to study that compactification. Let me mention one downside of that compactification. It's not a complex variety, and I'm admittedly a complex geometer, so I want to stay within the contexts of complex varieties. There's an announcement of a compactification by John Smalley, which hasn't appeared as a written object yet, which is also in the real world. It's not the complex compactification, not complex, but admits SL2R action. So the SL2R action that I'm not going into details, that is in the interior, has the advantage to extend to this compactification. So the compactifications I want to address, that there's a precursor in the same group of 5 authors, and there's a work in the process of writing down that I'll be really talking about. There is the incidence variety compactification, and this is this is a complex variety, and I'm telling you why this is an incidence variety compactification, and what is the general idea. So I'm passing again to this side of the blackboard. So on a smooth curve, we have the bundle of holomorphic one-forms. Over a stable curve, that bundle of holomorphic one-forms, it's a rank G vector bundles, it extends to stable curves, to so-called stable forms. So we have omega mg, which sits over mg, and this is inside the delinear-Mumford compactification, and there is mg in the delinear-Mumford compactification, which is the space of pairs x omega, and omega is a stable form. A stable form on a stable curve is a differential form that is holomorphic except for possibly simple poles at the nodes. And if we have simple poles, the residues of the two sides have to match up. That's the definition of a stable form. And this is still a vector bundle. And if we have a stratum here, we can, and of course this is inside here, we can just close it up in that space. Well, you might say this whole thing is not a compactification because this is a vector bundle rather than a projective bundle. But I'll be sloppy about that fact during the whole talk. In fact, you can just rescale the objects in here, at least, well, if I put a star for non-zero here and a star for non-zero here, then I can projectivize the objects by allowing rescalings. And then this is true and fully correct compactification. Here's your compactification. So why am I not going home? Well, because this compactification has a lot of downsides. In some sense, this compactification is a complex variety, but this is even retains much less information than this compactification. So in order to explain what's the problem here, let me show you what it means to degenerate if you go to the boundary. So let me come back to the example that was on the blackboard in Kazra's talk. So far, this is a translation surface of genus G. If I take that side and identify that side by parallel translation, and I continue to identify sides that have the same label. So that surface seems to be a surface of genus 2, but I want to do more. I want to cut in a little slit and take out a parallelogram of a certain size r here and a certain length L over there. And I want to identify this side number 5 to this side number 5 and this side number 6 to this side number 6. This is still a flat surface. And for the moment, I want to keep the sides of all side lengths fixed, except that I want to look at r that goes to 0. If I let r go to 0, well, Alex and Mariam would say, what you see is what you get. If r is 0, you don't see that anymore. That's what you get. So what you, in their compactification, you just get a surface of genus 2. Namely, that surface that sits around there. And we can argue about marked points separately. And don't want to get really into that. But the surface has had genus 3 before, so you shouldn't lose genus, you shouldn't lose too much of information. So what actually happens is, you might want to focus on those little neighborhoods of these 2 points. So let me cut it out of the neighborhood. That little neighborhood, well, if I'm taking the naive viewpoint, remember that height is called r. That goes to 0, and it seems that this whole neighborhood will just be 2 disks and period, and it's just gone. But I might take different glasses, and instead of that thing goes to 0, I rescale my whole viewpoint. Rescaling the whole viewpoint is, let's say R goes to 0 like t squared, t being a parameter. I could make my R to be of constant size by dividing everything by t squared, which goes to 0, and which then makes that all other parameters become extremely large. And then what I get here? Well, I get a piece of a Riemann surface which is now constant, and I want to maintain that surface. So that surface here, in fact, so the orange surface is this object. Here is the orange surface. It's not Pac-Man, it's the orange surface. This is, with that side, number 5 identified to that side, number 5, is an honest Riemann surface that you might want to keep track of. So suppose you have, so what's the picture that appears here? Well, this is a surface of X, a surface of genus 3, and when you degenerate, what happens geometrically, there is one big Riemann surface, and I'm now going back to the dual graph viewpoint that I was adopting here. There's one big surface, which is that surface of genus 2, and one surface here, which is a surface of genus, I'm putting here the genus equals 2, a surface of genus 0, which is all what is about to shrink. And there is 2 nodes connecting the 2. So suppose that surface was not as simple as genus as 0, but I don't want to draw it. Suppose that surface was genus 10 and had a lot of marked points and a lot of geometry in it. And that surface is also genus 10. If you just take what you see is what you get compactification, all the information about that surface is lost. So a basic reason why that compactification, that thing is not good, or why it loses a lot of information, and also this compactification loses a lot of information, is that is not good, and it's definitely not smooth, is because all topological information about subsurfaces where omega restricted to that subsurface tends to 0 is lost. Okay. Second attempt of making that better, and that's the viewpoint of that compactification. Such a differential form comes with its zeros. The zeros of a differential form, if I tell you the zeros of the differential form, and if I tell you to which order the differential forms vanish at that 0, you almost uniquely get the differential form back up to scale. So the next idea is retain the information about zeros. So if I have a point x omega, which is a translation surface, so it belongs to some stratum omega mg mu, I could map it I could map that point to just the moduli space of curves. Well, this would just retain x, but I also could, this maps just to x, but I also could map it to the moduli space of curves of genus G plus n marked points, where I map it to x and the zeros of omega. So mu is, in fact, in this case, a collection of n marked points, say of order m1 to mn. In that way, I retain way more information. I retain, at each component, for example, at such a component, I retain the differential up to a scaling factor. And I could do even more. I could also retain the holomorphic one form. The overall scale at sort of that top level component, I could keep it as well. So I could map to omega mgn. And of course, omega mgn, this is the collection of Riemann surfaces, holomorphic one forms, and points z1 to zn, z1 to zn. And the image of that thing consists of the points where, so the image consists of those points where the divisor of omega consists just of the sum mi zi. That's why we call it an incidence variety compactification. It's where the locus where the omega and the points z1 to zn are incident in the sense that they have this relation. Okay. That object, mgn, has a nice the linear Mumford compactification. I can take the bundle of stable forms in there. I can close it up. And the closure of a stratum in here, so let me sort of make the definition, is the closure of the stratum omega mg mu inside that space, the linear Mumford compactification of the moduli space of genus G curves with n marked points. There's a paper that you can find on the archive that describes you the image, and I'll tell you about that. To some extent, the main problem of that thing being this closure is anything. Is very much not smooth. Very not smooth. It has horrible singularities. The paper doesn't tell you, but I can prove to you nowadays that it has really, really bad singularities. So in order to perform many of these calculations that we're motivating, you want to find coordinates near infinity, where you perform, for example, intersection calculations. And you really want something where you understand the coordinates near infinity, and this is poorly possible in that compactification. That's why you want probably something smooth. So if you're an algebraic geometer, or complex algebraic geometer, you have maybe in your pocket Hironaka's proof of resolution of singularities, which tells you, hey, whenever you have an algebraic variety, and this is an algebraic variety, there is a resolution of singularities. So there is some finite procedure of blowing ups that makes the space smooth. So we can make a smooth compactification. Why am I not going home at that point? Because if you just do that blow-up process of just somehow blowing up, you have no idea what these points on those blow-up objects mean. Was that clever in board management? Well, to some extent. So the new thing is there. The theorem I want to mainly tell you about, not yet available in written form, but we have partially written it down. There is a smooth well, I'm writing and then explaining functorial compactification. That I want to call, yeah, psi mg mu for of any given stratum omega mg mu. Smooth, with the same caveat that I said before, that this is in fact the smooth orbifold or quotient singularities which come from the geometry. I'm going to explain functorial over the next 30 minutes what it really means. Well, that thing should indicate, the letter psi should indicate that there's various levels or various scales of the differential, which already started to appear on that blackboard, and I'm going to elaborate. Functorial really means it represents a functor, but what I'm going to develop for you is what is the meaning of the boundary objects here. The boundary objects have some meaning which is not as easily described as just being stable curves, but it's something like that. It's not just not some random objects, they have a meaning. Okay, in order to describe you the meaning of the boundary objects, let me go back to what happened in the incidence variety compactification. What are the boundary objects there? So this is a pretty concrete question. Characterization of boundary objects. So if I give you a certain stratum, what are the objects that live in the boundary? Well, the objects that live in the boundary are obviously have a bunch of obvious topological data. So there's topological data. First of all, there is the dual graph, because any object in the moduli space of curves already had that part of the topological data. Since we were also distributing, since we had one forms, we still know where the zeros of the one form go. So for example, in that case, there's one zero that sits here, and the second zero that should maybe get a different color, which is also not orange, well, maybe red. There's a second zero that sits here, so I could mark that graph by adding legs that retain the information where the zeros are sitting, and I could also write down what is the order of the zeros at those legs. So let me encode that into the datum of the dual graph. Plus legs that retain the information where the zeros are. More importantly, what happened in that degeneration process? There were surfaces that were degenerating not at all, like that surface here. And there were surfaces that were degenerating at a certain speed. For example, that subsurface was degenerating at the speed t squared. And I could make that, the whole object more complicated by adding yet another slit in here. Let me be simple, where I have a parameter R2, and R2 goes to 0 like t to the 4. So that part of the surface degenerates even more quickly. So in that case, I would have let me draw for that case that I drew now the corresponding object. It has still the surface of genus 2 that was on top. It has still that part of genus 0 that was going. This part was decaying at constant speed. I mean, it was not decaying at all. This part was decaying at order t squared. And finally, there's a part that was decaying decaying at order t to the 4, and topologically, this is the picture. This is also a genus 0 surface. So this being said, on the whole dual graph, there is an order, a dual graph plus legs, plus an order relation. Between any two components, I can judge who's on top of whom. Being on if somebody's on top of somebody else means that the one who's on top decays less quickly in size than the one who's on bottom. So, and on top meaning on top, and on bottom meaning on top, I'm indicating that order, that level structure. This is the same thing as a level structure. I'm indicating it by the way the surface is drawn at the blackboard. And there might be surfaces I could also say, well, let me do that. This one could also degenerate like t squared. Then this is t squared, and this is t squared, and they're on the same scale. That also happens. So the new example I was drawing here corresponds to this picture. I have two subsurfaces of genus 0 that decay on the same scale. So these are, these are two possible level graphs that indicate ways how this surface with the addendum now degenerates. And on these surfaces, the complex data, so the limiting object is x, is a stable curve. And, well, on the big surface, I definitely have a holomorphic one form. And after, well, on the small surfaces, the holomorphic one form is about to degenerate. But if I'm rescaling by the appropriate parameter, it stays of constant order of magnitude. So I get holomorphic one forms plus non-zero holomorphic one forms on each component. Let me call these holomorphic, non-zero holomorphic one forms eta and maybe eta v on each component v, of, or maybe xv of that stable curve if it acquires many components. And so eta v, the collection of eta v is not totally arbitrary. These eta v form what is called, what we call in that paper a twisted differential. Twisted is maybe in that situation not very well explained. It corresponds to the fact that that rescaling parameter can be viewed as twisting canonical bundles by line bundles, just to give you an idea where that word comes from. So form a twisted differential, and I'm telling you two important things, namely that this is a twisted meromorphic differential. Namely, this differential has poles. It may have poles, and so it has zeros and poles. So what happens if I squeeze that initial surface to the ambient big surface? It just looks regular on that part. Same thing here. So the differential eta 0 that sits on top level has along all the marked points that arise when I squash that surface, no zero, no poles, nothing. It has a 0 of order 0 here. And let's look at the complementary side. What kind of picture is that? If you see a picture of a differential like that, I mean, this is, you should really view it as the exterior of the plane. So that differential goes on in the whole plane. This is Open Strabel's book. This is the picture of a differential of a pole of order 2. So we have plenty of poles of order 2. In fact, in the simple example I drew, they are all of order 2. So the differential is a meromorphic differential satisfying a bunch of conditions, which I'm not going to explain in full detail, but I started to explain here now the matching order condition, namely that the order at the top end of a node plus the order at the bottom end of a node always adds up to -2. And if there is two residue conditions, one of them is the usual residue conditions, the usual residue condition for simple poles. So simple poles also arise. This is the case where there's two -1s that add up to -2, and this should happen if and only if the two components stay at the same speed. And there is the usual residue condition plus a condition which is called the global residue condition, which is the main thing, the main new ingredient in that paper, which is a property that the residues should satisfy that you should recognize from globally staring at the graph. I don't need it for now, so I will skip the precise description of that object. Okay. So what next? Why am I not happy with this? And what needs to be improved? And what's the reason for that object to be still singular? So why is the incidence variety compactification still singular? There's two sources why this happens. The first one is the following thing. So suppose I have something which is on top level, which stays of constant speed, and I have two components that degenerate with some speed. Say this is constant, this degenerates with the order of magnitude of t. And a bunch of nodes in between the two components. It might be 2 as in the example before, it might be 3 or 4 or whatever. So I might as well go back to the previous example and go back to the case where these, well, decay of the order of magnitude t. So there's two possibilities. Let me compare two possibilities. So either R2 is t and R1 is also t, or this is possibility A, and possibility B is R2 is 100 times t. If I just look at the limiting object will be the same in both cases. In fact, t is not, the limiting object, just that rescale differential, will be the same in both cases. But you might want to distinguish it. I mean, after all, the ratio between the two, which are on the same level, that's why they go both in the order of magnitude t. They could be 1, the ratio could be 100, the ratio could be 1 over 100, it could be any number. So you might want to distinguish also the rates with respect to which they converge. So, so said differently, the differential here, we have an eta 0 here, an eta v1 and an eta v2 on these two components. So these differentials here are in that definition. Only well-defined up to, these are well-defined, defined up to a scale. But what you really want to do is a compactification, where you maintain the possibility that they could be rescaled individually. Retain in the smooth compactification their relative scales. And the second source leads to a notion that in topological papers in that subject already has appeared, which is the notion about prong matchings. So let me recall the local geometry of a differential which has a zero of a certain order. So it's z to the k dz. Any differential with a zero of order k can be put locally into the form of zero of order k dz. And for the purpose of concreteness, let me draw just the case k equals 1. So locally, this differential, well, how many possibilities do I really want? Let me put z square over z dz. So then I have three horizontal axes. 3 horizontal axes, 3 outgoing prongs. On the other hand, such a differential z to the k dz should be paired by the matching order conditions with a pole differential which has a pole of order 4 in that form at the corresponding point. So this is z to the minus 4 dz. And in fact, the local form cannot get rid of the residue which might be there. So to be honest, let me put the residue, although it doesn't play a major role. And such a differential with a pole of order 4 looks like the exterior of that object. So it also has 3 prongs that go off to infinity. And so whereas the surface the piece of the surface I'm looking at is here the interior, here it's the exterior. So suppose now I'm giving you such a datum of a stable curve and a bunch of differentials and that satisfy all those conditions. And first of all, you're trying to prove that characterization in the incidence variety compactification. You're trying to prove that such an object sits in the boundary. How are you going to do that? You're going to do plumbing. So what does, so this shouldn't go on that blackboard. I should take a different blackboard to explain you the idea of plumbing and the relation to prong matchings. So plumbing means that if I have a surface which at some point has a node, I focus fully into that node, and near that node I may have maybe have 3 prongs, 1, 2, 3 outgoing rays as in the previous picture, and on the polar side I also have 3 outgoing rays as in the previous picture. And if I want to make from that surface a smooth surface, I'm gluing to that what is called the standard plumbing fixture. Standard plumbing fixture is a piece of a smooth surface which topologically looks like that, and algebraically I'm putting here x times y equals t for t different from 0, whereas this is x times y equal to 0. Well, I should maybe draw this a little closer to something, well, this is close to that object, and when you open it up, the 3 prongs just give 3 straight lines that go through. So now you see the form of ambiguity you have in that whole process. When you have a big surface, and this is part of a big surface, and this is part of a big surface, and you want to replace that part where that big surface has a node by something where the big surface is smooth, you have to chop that off and glue that thing in. And obviously, well, I can demonstrate with my hands, there are several possibilities how you can do that. You can do this, 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 this. In that particular case I was drawing here, this doesn't make much of a difference. Think of 2 balls. And if you glue it here or here or here, if there's just one node connecting the 2, that doesn't make much of a difference. You can turn the lower ball, right? But the very moment you have 2 nodes connecting the 2 surfaces, there's really some ambiguity. You can turn one, but not the other. And you can't undo that by turning the lower ball, except something happens simultaneously. So that's the problem with the prong matching. So a local prong matching is something that you want to do if you want to open up a node, if you want to smoothen. So prong matching is an identification well, if you identify one prong, then you know where all the others go. So you have to identify one prong from the upper side to one prong of the lower side, and then all the rest is determined cyclically. So why is that an issue to the object being smooth? Well, there's a pretty obvious one. Those think of 2 surfaces. Well, maybe I'm now adding a second cylinder joining the 2 surfaces. Think of 2 surfaces where in each of the 2 pieces I had 3 prongs. Here I have 3 prongs, and there I have 3 prongs. If I take the 2 surfaces, and here I glue in that version, and here I glue in the plumbing fixture in a twisted version, and I've been opening up the thing only a little bit, the 2 surfaces are, the complex structure of the 2 surfaces is pretty far away from one from another. You can track that by computing periods. So these objects should be really far away if the moduli space were smooth. So if you don't keep track if you don't treat these objects with different possibilities of prong matchings differently, locally the moduli space, this causes normal, non-normal singularities. I should say branches crossing. Branches that cross and that in the normalization have to be separated. They have to be taken apart. They have to be far away. So given all that, I can make the statement of the theorem, which went here, functorial compactification of that modular space somewhat more precise by saying that points in that space omega mg mu correspond to, well, you'd have to give a name to that object. We call them multi-scale differential. differentials, which is the same thing as a twisted differential. This is equal to a twisted differential. A differential for a certain level graph. Plus prong matchings at each node. Prong matchings at each node. At each node. Somehow this is this intermediate notion is what you might call prong match differentials, and we do so. And a lot of the subtlety of the whole thing goes into understanding what the equivalence relation between these objects should be. So this equivalence relation, there's an equivalence relation between these objects, which very coarsely can be explained by the fact that for twisted differentials, I could multiply the objects at each level by a scalar multiple. Sort of that equivalence relation is still there. But when multiplying things by a scalar multiple on each level, you shouldn't be too coarse. You shouldn't throw all them in one box. Things that multiply but turn one prong matching into the next one with a given root of unity. This should really be still be considered a different object. So in that sense, the equivalence relation works with a certain torus, which is C star to the number of levels, and it's a covering of the obvious torus by a group that is determined by the possibilities of prong matchings. So let me end by completing the theorem, saying that this is not only smooth in the obvious sense, but that also the boundary structure is as nice as for the linear Mumford compactification, namely with this is a normal crossing boundary divisor, which is nice in the sense that you exactly know what the codimension of a certain object is. So for example, the codimension of a boundary object is exactly the number of levels minus 1. That object has one level, minus 1 is 0. That object has codimension 0. This corresponds to a smooth point. This is a generic point. That object has 2 levels, so there's one level passage. So this parameterizes an object that sits in the codimension 1 boundary. This is the principal boundary the Eskin-Mazur-Zorich compactification was alluding to. And this object has 2 level passages. So this is sits in a codimension 2 boundary. You can either smoothen that part, or you can smoothen that part in order to reduce the number of levels by 1, and then you do the other thing to become generic. So retain as information, in order to smoothen things in the moduli space of curves, you can just smoothen nodes. The number of nodes gives you the codimension you're in when looking at a stable curve. If you're in that compactification of the moduli space of strata, you should smoothen level passages. For each level passages gives you one codimension. And in that sense, that space is very nice. Didn't say anything about the construction, which passes through augmented Teichmuller space and works the way down Dehn space, and well, the complex analytic approach to the construction of moduli space. Thank you for your attention.
Are there any questions? Okay, then let's thank our speaker again.